Right now, as you settle into the warmth of your evening beneath the frozen surface of Antarctica's ocean, something that seems impossible is happening. A finger of ice is reaching down from the frozen ceiling above, growing toward the seafloor like a deadly stalactite made of frozen brine. Everything it touches dies instantly, frozen solid in a spreading web of ice that creeps across the ocean floor. This is a brinicle, perhaps the strangest and most lethal phenomenon in Earth's oceans. It's ice that forms underwater, death that flows downward like a frozen waterfall, a killing frost that spreads beneath the sea where frost shouldn't exist. Imagine ice that behaves like lava, flowing, spreading, consuming everything in its path. But instead of heat bringing death, it's an impossible cold, a freeze so intense it turns seawater solid in seconds. The creatures of the seafloor, starfish, sea urchins, small fish, they have no warning, no time to escape. One moment they're alive, the next they're entombed in ice, frozen statues in an underwater gallery of death. The first humans to witness brinicles forming could barely believe their eyes. How could ice grow underwater? How could it flow like a liquid while freezing everything solid? How could something so beautiful be so deadly? Tonight, we're going to descend beneath the polar ice, into waters so cold they push the boundaries of what's possible, to explore these fingers of death that reach down from above, these brinicles that seem to violate the very laws of physics. To understand brinicles, we must first understand the alien world where they form, the waters beneath polar sea ice, particularly around Antarctica. These are not ordinary oceans. The water temperature hovers around -1.9 degrees Celsius, 28.6 degrees Fahrenheit, just barely above the freezing point of seawater. The water is so cold that most fish would freeze solid, their blood turning to ice crystals. The few creatures that survive here have antifreeze proteins in their blood, chemical adaptations that prevent ice from forming in their bodies. Above, a ceiling of sea ice stretches to the horizon, anywhere from 1 to several meters thick. This isn't solid ice like a skating rink, but a complex porous structure full of tiny channels and pockets. The ice is alive with chemistry, constantly freezing and melting, expanding and contracting. So the boundary between ice and ocean is not a simple line but a gradient, a zone of exchange where salt and fresh water, solid and liquid, meet in ways that create some of Earth's strangest phenomena. Light barely penetrates here. What little sunlight filters through the ice above creates an eerie, blue-green twilight. It's a world of perpetual dusk, where the normal rules of Earth's surface don't apply. Seawater doesn't freeze like fresh water. When fresh water freezes at 0 degrees Celsius, it forms pure ice. But seawater, with its dissolved salts, behaves differently. As seawater begins to freeze, something remarkable happens. The ice crystals that form are pure water, A-O without salt. The salt is excluded, rejected by the growing ice crystal structure. This rejection of salt is the key to understanding brinicles. When sea ice forms on the ocean surface, it traps pockets of highly concentrated brine, water so salty it can't freeze at normal seawater temperatures. This brine can be 5 times saltier than normal seawater, with salt concentrations reaching 25% or higher. This super-saline brine has 2 critical properties. It's much denser than regular seawater. It has a much lower freezing point, remaining liquid, at temperatures that would freeze normal seawater solid. These pockets of brine sit within the sea ice, like liquid veins in a frozen body. They're at the same temperature as the ice around them, perhaps -20 degrees Celsius or colder, but they remain liquid because of their extreme salinity. Picture the underside of sea ice, an inverted landscape of ridges and valleys, frozen stalactites and hollows. Within this icy ceiling, channels of super-cooled brine percolate downward, driven by gravity. Below, the seafloor is covered with slow-moving creatures, adapted to the cold: starfish, sea urchins, anemones, small fish. They've evolved to survive in near-freezing water, but they're not prepared for what's about to descend from above. The conditions are perfect: extremely cold air above the ice, porous sea ice, full of brine channels, calm water below. All that's needed is a trigger, a crack, a channel, a pathway for the brine to escape. And then it begins. A brinicle begins with a breach, a crack, or hole in the sea ice that allows the super-cooled brine to escape into the ocean below. This might be caused by the ice shifting, cracking under pressure, or simply the brine channels finally connecting to form an exit. The brine that emerges is extraordinary. Temperature, -20 degrees Celsius or colder. Salinity, 200 plus parts per thousand. Normal seawater is 35. Density, significantly heavier than surrounding water. When this super-cooled super-saline brine meets the relatively warm seawater at -1.9 degrees Celsius, the temperature difference causes the seawater to freeze instantly. But this isn't normal freezing. It's shock freezing, so rapid that ice forms in sheets and tubes rather than crystals. The brine, being denser than seawater, sinks. As it sinks, it freezes the water around it, creating a tube of ice, a hollow chimney through which more brine can flow. This ice tube protects the brine stream from mixing with the warmer water, allowing it to maintain its deadly cold temperature as it descends. As more brine flows down through the newly formed ice tube, the brinicle grows longer, reaching toward the seafloor like a frozen finger. The process is self-reinforcing. Brine flows down through the tube. The super-cold brine freezes more seawater at the tip. The tube extends downward. More brine follows the path of least resistance through the tube. The cycle continues. The growth can be remarkably fast. Under ideal conditions, a brinicle can grow several meters in just a few hours. Time-lapse footage shows them descending like slow-motion lightning bolts, twisted and gnarled, following the path of the flowing brine. The ice tube itself is fragile, just millimeters thick in places. It's not solid ice, but a delicate shell, like a frozen soap bubble stretched into a tube. Inside, the river of death continues to flow. The structure of a brinicle is more complex than it first appears. It's not a simple tube but a sophisticated formation with multiple layers. The inner channel, the hollow core through which brine flows, typically a few centimeters in diameter. The ice wall, the frozen seawater forming the tube, usually 1-5 millimeters thick, porous and fragile. The boundary layer, a gradient zone, where the ice meets liquid water, constantly freezing and dissolving. The brine plume, the spreading pool of dense brine that flows from the tube's tip. The entire structure is dynamic, constantly changing. New ice forms at the growing tip, while older sections might crack or partially dissolve. The brine flow can vary, sometimes trickling, sometimes surging, causing the brinicle to grow in spurts. The most dramatic moment comes when a brinicle reaches the seafloor. The super-cooled brine, no longer constrained by its descent, spreads outward in a deadly pool. This brine is still far below the freezing point of seawater. As it flows across the bottom, it freezes everything it touches. The effect is immediate and lethal. A web of ice spreads across the seafloor, extending outward from the brinicle's base like frozen lightning crawling through water. Slow-moving creatures, starfish, sea urchins, bottom-dwelling fish, are caught in this spreading freeze. They have no time to react. The ice encases them in seconds, freezing them solid while they're still alive. Their cellular fluids turn to ice crystals, rupturing cell membranes, causing instant death. The BBC's filming of this phenomenon for their Frozen Planet series in 2011 provided the first widely seen footage of brinicle formation. Camera operator Hugh Miller described it. It was like watching death itself reaching down from above. The starfish were trying to move away, but they were too slow. The ice just consumed them. The brine river that creates and feeds a brinicle is a unique phenomenon. It's liquid, but colder than ice. It flows like water, but freezes everything it touches. It's denser than the surrounding seawater, so it sinks in pools and depressions on the seafloor. This river can flow for hours or even days, as long as the brine pocket in the ice above continues to drain. The volume can be substantial. A large brine pocket might contain hundreds of liters of super-saline water. As the brine flows, it creates a trail of death. The path of a brinicle across the seafloor can be traced by the frozen corpses it leaves behind, a macabre map of its journey, written in ice and death. The ice that forms when brinicle brine meets the seafloor isn't like normal ice. It's a complex mixture of ice crystals and trapped brine, forming structures that can be surprisingly elaborate. Ice flowers, delicate, flower-like formations that grow upward from the frozen pool. Ice sheets, thin layers that spread horizontally, following the seafloor's contours. Ice tubes, secondary brinicles, that form when brine finds new paths upward through the ice sheet. Ice caves, hollow spaces where the brine has pooled and then drained away, leaving frozen shells. This ice garden of death can cover several square meters around a single brinicle. In areas where multiple brinicles form, the entire seafloor can become a frozen wasteland, devoid of life, except for the occasional scavenger that arrives after the freeze has passed. The formation of ice underwater seems to violate our intuition. We expect ice to float, water to remain liquid underwater, but brinicles exploit a loophole in physics. The key is the relationship between salinity, temperature, and freezing point. Pure water freezes at 0 degrees Celsius. Seawater, with average salinity, freezes at about -1.9 degrees Celsius. But the super-saline brine inside sea ice doesn't freeze until it reaches -21 degrees Celsius or colder. When this -21 degrees Celsius brine meets -1.9 degrees Celsius seawater, the temperature difference is enormous, nearly 20 degrees. The seawater is actually hot compared to the brine. This temperature gradient drives rapid heat transfer, causing the seawater to freeze instantly. It's similar to pouring liquid nitrogen at -196 degrees Celsius into room temperature water. The water freezes instantly, not because it's cold in absolute terms, but because it's warm relative to the liquid nitrogen. Density differences are the engine that powers brinicle formation. The super-saline brine is much denser than regular seawater, sometimes 1.2 times denser or more. This density difference creates a powerful downward flow. The physics is similar to a waterfall, but instead of water falling through air, it's dense brine falling through less dense seawater. This density-driven flow is so strong it can maintain itself against currents and turbulence. The brine stream punches through the water column like a liquid drill, freezing a protective tube around itself as it goes. The energy dynamics of brinicle formation are fascinating. Freezing releases energy, heat of fusion, but this energy is quickly absorbed by the vast reservoir of super-cold brine. The system maintains a steady state where heat flows from seawater to brine. Seawater loses enough heat to freeze brine, gains heat, but remains below seawater's freezing point. The process continues as long as brine flows. This creates a heat pump of sorts, extracting thermal energy from the already cold seawater and transporting it away in the flowing brine. It's one of nature's most efficient freezing mechanisms. Despite their lethality, brinicles are part of the polar marine ecosystem. Some organisms have evolved to coexist with them. Icefish, Antarctic fish with antifreeze proteins can survive near brinicles, though direct contact is still fatal. Mobile predators, seals and penguins hunt in brinicle zones, taking advantage of the concentrated prey frozen by brinicles. Scavengers, amphipods and other scavengers feed on creatures killed by brinicles, cleaning up the frozen remains. Bacteria, specialized bacteria thrive in the high salinity environment around brinicle bases. Some creatures have developed strategies to avoid brinicles. Vertical migration. Many organisms move up in the water column when brinicles are forming, avoiding the seafloor killing zones. Rapid burial. Some worms and clams can quickly burrow into sediment when they detect the temperature drop that precedes a brinicle. Chemical detection. Certain species might detect the chemical signature of approaching brine and flee. Seasonal avoidance. Some animals migrate away from brinicle-prone areas during peak formation seasons. Brinicles play a complex role in polar ecosystems. Nutrient cycling. They concentrate nutrients in brine pools, creating feeding opportunities for specialized organisms. Habitat creation. Old brinicle ice formations create three-dimensional structures that some creatures use for shelter. Population control. They limit populations of slow-moving bottom dwellers, preventing overgrazing of seafloor algae. Carbon sequestration. The brine rivers carry dissolved carbon to the deep ocean, contributing to long-term carbon storage. Brinicles were first observed in the 1960s, but they were so strange that early observers weren't sure what they were seeing. Divers under Antarctic ice reported ice stalactites growing downward but were met with skepticism. Dr. Seeley Martin, studying sea ice in the 1970s, was among the first to understand the mechanism. He realized that brine drainage from sea ice could create these formations, but it took decades for his theories to be confirmed. The name brinicle was coined in the 1990s, a portmanteau of brine and icicle that perfectly captures their nature. Before that, they were called ice stalactites or brine channels, terms that didn't fully convey their dynamic, deadly nature. Documenting brinicles proved extraordinarily difficult. They form in remote, dangerous locations. The water is lethally cold for humans. They're unpredictable and temporary. They require specialized equipment to film. The BBC team that captured the first high-quality footage spent months preparing. They used time-lapse cameras in insulated housings, special lighting that wouldn't disturb the formation process, and teams of support divers working in shifts. Hugh Miller and Doug Anderson, the cameramen who filmed brinicles for Frozen Planet, described it as one of the most challenging shoots of their careers. They could only stay in the water for 30 minutes of 40 minutes at a time before hypothermia became life-threatening. The clear footage of brinicles revolutionized understanding of sea ice dynamics. Scientists realized that brinicle formation was more common and more important than previously thought. Research accelerated. Brinicles were found to be major factors in ocean mixing. They contribute significantly to deep water formation. They affect global ocean circulation patterns. They play a role in climate regulation. What seemed like a curiosity became recognized as an important oceanic process. Brinicles are sensitive indicators of climate change. As polar temperatures rise, frequency changes. Warmer conditions might reduce brinicle formation in some areas while increasing it in others where new sea ice forms. Intensity variations. Changes in ice thickness and salinity affect brinicle size and duration. Geographic shifts. Brinicles might form in new locations as ice patterns change. Ecosystem disruption. Changes in brinicle patterns affect the organisms that have adapted to them. Scientists now monitor brinicle formation as one indicator of polar ocean health. Brinicles contribute to the formation of Antarctic bottom water, the coldest, densest water in the oceans. This water drives global ocean circulation, affecting climate worldwide. The brine rejected during sea ice formation, concentrated and delivered to depth by brinicles, increases water density. This dense water sinks, flowing along the ocean floor and eventually rising elsewhere, creating a global conveyor belt of ocean currents. Changes in brinicle formation could affect global heat distribution, nutrient cycling, oxygen distribution in deep oceans, climate patterns worldwide. Brinicles play a surprising role in carbon sequestration. The super-saline brine carries dissolved CO from the surface to the deep ocean. Once there, this carbon can remain trapped for centuries or millennia. This brinicle carbon pump might sequester millions of tons of carbon annually. As we seek ways to remove CO from this atmosphere, understanding natural processes like brinicle formation becomes crucial. We still don't fully understand what triggers brinicle formation at specific times and places. Why does one brine channel become a brinicle while another doesn't? What determines when a brinicle starts growing? Factors might include microscopic ice crystal structure, precise temperature gradients, water current patterns, biological activity, random quantum fluctuations in ice formation. The complete answer remains elusive. How large can brinicles grow? The longest observed was about 5–6 meters, but theoretical models suggest they could grow much longer under ideal conditions. Factors limiting size might include brine supply depletion, structural collapse under their own weight, current disruption, temperature changes, seafloor contact. Giant prehistoric brinicles might have existed when ice ages created thicker sea ice with larger brine reservoirs. Could any form of life thrive specifically in brinicle environments? The extreme conditions, high salinity, extreme cold, rapid freezing, push the boundaries of habitability, yet we found life in similarly extreme environments. Bacteria in Antarctic ice, organisms in deep-sea brine pools, life in nuclear reactor cooling pools. Perhaps specialized organisms exist that not only survive brinicles but depend on them. Brinicles embody a troubling paradox. They're simultaneously beautiful and deadly. Their formation creates stunning ice sculptures, delicate and intricate. Time-lapse footage reveals an almost artistic process, like nature painting with frozen death. This duality appears throughout nature. Volcanic eruptions that destroy but create new land, hurricanes that devastate but redistribute ocean heat, forest fires that kill but regenerate ecosystems. Brinicles remind us that nature's beauty often comes paired with danger, that creation and destruction are often the same process, viewed from different angles. Brinicles operate according to physical laws, thermodynamics, fluid dynamics, chemistry. They don't choose their victims, or spare the innocent. They simply follow the equations. This mechanical indifference can be disturbing. The starfish frozen by a brinicle dies not from malice but from mathematics. The brinicle doesn't care about the ecosystem it disrupts or the lives it ends. Yet this same indifference makes brinicles predictable, understandable, ultimately manageable. We can study them, model them, perhaps eventually predict them. Brinicles seem massive to the creatures they kill, towering columns of death descending from above. But to us, they're delicate, fragile formations. To the ocean, they're microscopic. To the planet, they're invisible. This scale relativity reminds us that significance depends on perspective. What's catastrophic at one scale might be trivial at another. What seems permanent might be temporary when viewed across different time scales. Arctic indigenous peoples have long known about strange ice formations under the sea, though their traditional knowledge hasn't always been recognized by Western science. Inuit elders describe ice that grows downward zones where fish die mysteriously, times when the sea floor becomes dangerous, seasonal patterns of underwater ice formation. This traditional knowledge passed down through generations, preceded scientific discovery by centuries. Since their filming, brinicles have captured public imagination. Nature documentaries, featured in multiple series as examples of extreme natural phenomena. Science fiction, inspired alien life forms and hostile environments in various media. Video games, appeared as environmental hazards in underwater exploration games. Climate fiction, used as symbols of nature's power and fragility in climate change narratives. Brinicles have become teaching tools for phase transitions and states of matter density and convection, extreme environments and adaptation, climate systems and ocean circulation. The relationship between beauty and danger in nature. They're perfect examples of how complex phenomena emerge from simple physical principles. Scientists worldwide are studying brinicles' formation dynamics, using high-speed cameras and sensors to understand formation in detail. Chemical analysis, examining the precise composition of brinicle brine in ice. Biological surveys, cataloging organisms affected by and adapted to brinicles. Climate modeling, incorporating brinicle effects into ocean and climate models. Remote sensing, developing ways to detect brinicles from above using satellites and drones. Upcoming research will explore artificial brinicle creation for study brinicle formation on other worlds. Europa. Enceladus, biomimetic applications of brinicle processes. Brinicle prevention in polar infrastructure. Historical brinicle activity in ice cores. Understanding brinicles might lead to new refrigeration technologies, improved desalination methods, better sea ice prediction, models novel materials inspired by brinicle ice techniques for underwater construction in polar regions. I first learned about brinicles through a grainy video clip shared online. The footage was poor quality, but something about it captured my attention. Ice growing downward underwater, reaching toward the seafloor like a skeletal finger. It seemed impossible, like someone had reversed the footage. Ice should float up, not grow down. Water shouldn't freeze underwater. Yet there it was, defying my assumptions about how the world works. Learning about brinicles changed how I think about extremes. Life exists at boundaries we can barely imagine. What seems impossible might just be unfamiliar. Processes, simple rules, temperature, density, salinity, can create complex, beautiful, deadly phenomena. Scales, what's catastrophic for one creature might be insignificant to another. Knowledge. How much remains unknown. Even on our own planet, brinicles haunt my imagination. The thought of being a seafloor creature, watching death descend from above, unable to escape, frozen alive, it's nightmarish, yet they're also wonderful. The physics is elegant. The formations are beautiful. The ecosystem adaptations are remarkable. They're reminders that Earth still holds mysteries, that nature still surprises us. Tonight, as you lie warm in your bed, picture the polar seas, beneath kilometers of ice. In permanent darkness, brinicles are forming right now. Somewhere, brine is beginning to leak from ice above. A tube is starting to grow. Death is descending toward unsuspecting creatures. Ice is spreading across a seafloor that shouldn't freeze. This is happening now. Has been happening for millennia. Will continue long after we're gone. It's a process indifferent to observation, continuing whether we watch or not. There's comfort in knowing brinicles are far away, confined to the polar seas. They can't reach you. They're not under your bed or in your bathtub. They require conditions so specific that most of Earth's oceans can't support them. Yet knowing they exist somewhere makes the world stranger, more dangerous, more interesting. Your planet has fingers of death growing beneath its ice. Your oceans hide formations that kill by freezing. Your world is more alien than you knew. You might dream of brinicles tonight, descending through blue-green water, spreading across the seafloor, freezing everything they touch, growing, reaching, killing. These dreams connect you to Earth's extremes, to places humans rarely go, to processes we've only recently discovered. When you wake tomorrow, warm and safe, remember, brinicles are forming right now. Creatures are dying, frozen instantly. Ice is growing where it shouldn't. Physics is creating beauty and death simultaneously. This knowledge makes your warmth more precious, your safety more apparent, your world more mysterious. Brinicles remind us that beauty and death often intertwine. The same process that creates stunning ice formations kills without mercy. The same physics that makes snowflakes makes weapons of ice. This isn't a flaw in nature, but a feature. Creation and destruction are often the same force applied differently. The universe doesn't separate aesthetics from effect. Life adapts to brinicles, avoids them, survives them, even exploits them. This adaptation showcases life's incredible flexibility. If life can adapt to fingers of death descending from above, what can't it adapt to? What environment is truly uninhabitable? What challenge is insurmountable? Brinicles remind us how recently we've discovered them, how much remains unknown. They formed for millions of years before we knew they existed. What else is happening right now that we haven't discovered? The planet we think we know still surprises us. The oceans we've mapped still hide mysteries. The ice we've studied still reveals new phenomena. To a starfish, a brinicle is apocalyptic. To us, it's fascinating. To Earth, it's trivial. To the universe, it's nothing. This scale relativity applies to everything. Our catastrophes, triumphs, fears, all depend on perspective. What seems world-ending might be world-building at a different scale. Brinicles are real. They form when super-saline brine drains from sea ice into ocean water. They create tubes of ice that grow downward. They freeze and kill seafloor creatures. They're part of ocean circulation and climate systems. These are facts, observed and documented. We wonder, how many creatures have brinicles killed over geological time? Could brinicles form on other worlds with under-ice oceans? What organisms might specialize in brinicle environments? How will climate change affect brinicle formation? What other phenomena remain undiscovered in polar seas? Brinicles invite us to appreciate Earth's hidden extremes. Respect the power of simple physics. Consider beauty and danger as linked. Remember that discovery continues. Stay curious about our planet. You're now connected to the brinicles. When you think of ice, you'll remember ice that kills. When you consider the ocean, you'll think of fingers of death. When you appreciate warmth, you'll recall the deadly cold. This connection enriches your understanding of Earth. You know about one of its strangest phenomena. You carry knowledge of beauty that kills, ice that shouldn't exist, death that flows like water. Find peace in knowing brinicles exist. They're part of Earth's complexity, its capacity for surprise, its indifference to our assumptions. They'll continue forming whether we watch or not. They'll keep killing, creating, mystifying. They're eternal. As long as polar seas exist, as long as ice meets ocean, as long as physics remains physics. Tonight, sleep peacefully, knowing that far away in the coldest seas, fingers of ice are reaching down through dark water, creating death and beauty in equal measure. Tomorrow, wake grateful for warmth, for distance from polar seas, for a world that still surprises us with phenomena like brinicles. They are Earth's strangest ice, death flowing like water, beauty freezing life solid, physics creating impossibility. The brinicles, the fingers of death, the ice that shouldn't be, forever forming in the cold dark, forever reaching downward, forever freezing the seafloor, forever reminding us that Earth is stranger than we know. Scientists have successfully created brinicles in laboratory settings, revealing details impossible to observe in nature. These experiments require precise control of temperature, salinity, and pressure. Martin Chaplin at London's South Bank University developed a technique using a tank of seawater cooled to -2 degrees Celsius. By slowly dripping super-cooled brine from above, his team created miniature brinicles just centimeters long, but structurally identical to their natural counterparts. The laboratory observations revealed surprising details. Pulsating growth. Brinicles don't grow smoothly, but in pulses with periods of rapid extension followed by pauses. This pulsation corresponds to variations in brine flow rate. Self-healing. When damaged, brinicles can repair themselves if brine flow continues. New ice forms to seal cracks, maintaining the tube's integrity. Branching patterns. Under certain conditions, brinicles branch like trees, creating multiple tubes from a single source. These branches follow mathematical patterns similar to lightning or blood vessels. Temperature gradients. Precise measurements show temperature can vary by 15 degrees Celsius over just a few millimeters near a growing brinicle tip, one of the steepest temperature gradients in nature. Remarkably, you can create a simple analog of a brinicle in your kitchen. Fill a container with very salty warm water. Carefully place ice cubes made from fresh water on top. As the ice melts, the cold fresh water, being less dense than the salt water, creates visible streams descending through the salt water, a density-driven flow similar to brinicle formation. While this doesn't create ice tubes, it demonstrates the density-driven flow that powers brinicles. Add food coloring to the ice, and you can watch the brinicle descend through the water, pooling at the bottom like the deadly brine. Laboratory experiments revealed that pressure significantly affects brinicle formation. At greater depths, where pressure is higher, brinicles form more slowly, but are more stable. The ice tubes are denser and stronger. The brine remains liquid at even lower temperatures. The killing zone at the brinicle's base is larger. This explains why brinicles in shallow water, less than 20 meters, tend to be thin and fragile, while those in deeper water, 50+ meters, can be thick and robust enough to survive for weeks. Brinicles exhibit fractal properties, patterns that repeat at different scales. The branching of large brinicles mirrors the branching of microscopic ice crystals within them. This self-similarity appears at scales from millimeters to meters. Mathematician Dr. Kenneth Librecht, studying brinicle structure, found they follow power laws similar to other natural phenomena: river networks, lightning bolts, blood vessels, tree branches. The mathematical equation describing brinicle growth rate is L equals sine K quarts thou cotters S quarts T circumflex 1/5, where L equals sine brinicle length, K equals sine constant, depending on local conditions, 1T equals sine temperature difference, S equals sine salinity difference, equals sine time. This equation, while simplified, captures the essential physics and has proven remarkably accurate in predicting brinicle growth. Brinicle formation is a chaotic system. Tiny changes in initial conditions lead to vastly different outcomes. A temperature difference of 0.1 degrees Celsius, or a salinity variation of 1%, can determine whether a brinicle forms or not, grows straight or branches, survives or collapses. This chaos makes precise prediction impossible, but statistical prediction reliable. We can't say exactly where a brinicle will form, but we can predict the probability of formation given certain conditions. Brinicles are information-rich structures. Their shape, composition, and internal structure record the history of their formation. Growth rate variations show in ice layers. Temperature fluctuations create density variations. Salinity changes alter crystal structure. Current patterns leave spiral marks. Scientists can read a brinicle like tree rings, extracting information about past ocean conditions. A single brinicle contains thousands of data points about temperature, salinity, and currents during its formation. Jupiter's moon Europa, with its subsurface ocean beneath an ice shell, might host brinicles far larger than Earth's. The conditions are surprisingly similar: ice ceiling above liquid ocean, temperature gradients, dissolved salts, tidal heating, creating brine pockets. Models suggest European brinicles could be hundreds of meters long, descending through the ocean like massive frozen waterfalls. These alien brinicles might play a crucial role in mixing Europa's ocean, potentially affecting the moon's habitability. Dr. Brittany Schmidt, studying Europa's ice dynamics, states, if brinicles exist on Europa, they could be transportation highways for nutrients, and possibly life between the ice shell and the ocean. They're not just killing mechanisms but potentially life-supporting structures. Saturn's moon Enceladus shoots geysers of water into space from its south pole. These geysers originate from a subsurface ocean, and the process might involve inverse brinicles, tubes of ice forming upward through the ice shell. As warm water rises through the ice, it could create ascending brinicle-like structures. These reverse brinicles might be the channels through which water reaches the surface and erupts into space. On Saturn's moon Titan, with its methane lakes and ethane rain, a different kind of brinicle might exist. When methane ice forms on hydrocarbon lakes, it could create hydrocarbon brinicles, fingers of frozen methane descending through liquid ethane. These would operate on the same principles as water brinicles, but at -180 degrees Celsius with completely different chemistry. They might create exotic ice formations unlike anything on Earth. Evidence suggests Mars once had northern oceans beneath ice sheets. If so, Martian brinicles might have existed billions of years ago. Geological formations resembling brinicle scars have been identified in regions thought to be ancient seafloors. These fossilized brinicles, if confirmed, would provide evidence of Mars's oceanic past and clues about the planet's climate history. Over millions of years, brinicles have been a consistent evolutionary pressure in polar seas. Organisms have evolved remarkable adaptations. Chemical detection. Some amphipods can detect the chemical signature of approaching brine from meters away, giving them time to escape. Rapid locomotion. Certain brittle stars have evolved quick-twitch muscle fibers specifically for escaping brinicles. They can move 10 times faster than related species in warmer waters. Protective shells. Some mollusks in brinicle zones have thicker shells with special proteins that resist ice crystal formation. Behavioral adaptations. Schools of fish have been observed posting sentinels that watch for brinicles while others feed. Metabolic adjustments. Some bacteria can switch to a cryptobiotic state when brinicle conditions are detected, essentially pausing their life processes until danger passes. Despite their lethality, brinicles create unique ecological niches. Brinicle specialists. Organisms adapted to high salinity thrive in the brine pools left by brinicles. Ice garden grazers. Some species feed on algae that grow on old brinicle ice formations. Scavenger specialists. Certain species specialize in quickly consuming brinicle victims before they decay. Chemosynthetic bacteria. Bacteria that use chemical energy from brine CO2 reactions form the base of brinicle-associated food webs. These specialists wouldn't exist without brinicles. Death-dealing formations have created opportunities for life. Brinicles and polar marine life are locked in a coevolutionary dance. Organisms evolve better detection and escape mechanisms. This creates selection pressure for faster-forming brinicles. Faster brinicles select for even better escape mechanisms. The cycle continues, driving innovation on both sides. This coevolution has produced some of the most sophisticated predator avoidance behaviors in the ocean. Even though the predator is just physics in action, brinicles leave signatures in ocean sediments that persist for millennia. These signatures include chemical traces. Distinctive ratios of salt isotopes mark where ancient brinicles touched the seafloor. Death assemblages. Concentrated fossils of brinicle victims create distinctive layers in sediment cores. Ice scars. Physical impressions where large brinicles scraped or compressed the seafloor. Brine channels. Fossilized channels in ancient sea ice, preserved in unique geological conditions. By studying these signatures, scientists can reconstruct past sea ice extent and thickness, ancient ocean temperatures and salinity, historical frequency of brinicle formation, climate variability over thousands of years. Analysis of brinicle signatures and sediment cores has revealed ice age intensity. During glacial maxima, brinicle formation was 100 times more frequent than today. Rapid climate shifts. Changes in brinicle frequency mark abrupt climate transitions. Ocean circulation changes. Variations in brinicle-produced deep water correlate with major ocean current reorganizations. Extinction events. Some polar marine extinctions coincide with periods of extreme brinicle activity. This paleoclimate record helps predict future changes. As climate warms, brinicle patterns will shift, potentially triggering cascading ecosystem changes. Brinicles affect carbon sequestration in ways we're only beginning to understand. They transport surface carbon to depth rapidly. They create conditions that preserve organic matter and sediments. They influence phytoplankton populations that absorb CO2. They affect the efficiency of the biological pump. Over geological time, brinicles might have sequestered gigatons of carbon, affecting Earth's climate on million-year timescales. Engineers are studying brinicles for technological applications. Self-assembling structures. Brinicles demonstrate how complex structures can self-assemble from simple ingredients. This inspires self-building materials for construction in extreme environments. Efficient heat exchangers. The rapid heat transfer in brinicles suggests designs for ultra-efficient cooling systems, desalination technology. The salt rejection mechanism of brinicle formation might lead to new water purification methods, cryogenic preservation. Understanding how organisms survive near brinicles could improve organ preservation techniques, flow control systems. The self-reinforcing tube formation of brinicles inspires designs for fluid control in industrial processes. Brinicle formation principles are being applied to robotics, self-healing robots that can repair damage by growing new structural elements, like brinicles self-heal. Adaptive architecture, buildings that respond to environmental conditions by growing or reshaping structural elements. Exploration vehicles, probes for exploring icy moons that use brinicle-like processes to melt through ice shells. Mining technology, equipment that uses controlled brinicle formation to extract minerals from seawater. Phase transition management. Brinicles demonstrate controlled phase transitions that could revolutionize manufacturing. Do brinicles have agency? They seem to choose paths, seek victims, grow toward targets. Of course, they're just following physics. But so are we. Where's the line between mechanical process and agency? This question becomes practical when programming robots or AI. If we create machines that form structures like brinicles, following simple rules but creating complex behaviors, at what point do they become agents rather than processes? Brinicles seem purposeful. They efficiently freeze seafloor creatures, contribute to ocean circulation, sequester carbon, but they have no purpose, just consequences. This mirrors larger questions. Does nature have purpose, or do we project purpose onto purposeless processes? Are brinicles for killing, mixing oceans and storing carbon, or do they just happen to do these things? Why do we find brinicles beautiful? They're instruments of death, yet their formation is mesmerizing, their structures elegant. This aesthetic response to deadly phenomena appears throughout human experience. Perhaps beauty isn't about benefit, but about pattern recognition, complexity, and surprise. Brinicles combine all three, triggering our aesthetic sense, regardless of their lethality. Now that we know about brinicles, do we have responsibilities? Should we protect brinicle habitats? Warn vulnerable species? Use brinicle knowledge for human benefit? Knowledge creates obligation. Understanding brinicles makes us stewards of that knowledge, responsible for how it's used or ignored. Brinicles have inspired science fiction scenarios, alien weapons. Stories feature weaponized brinicles on ice worlds. Terraforming tools, brinicles used to modify ocean chemistry on colonized planets. Communication methods, aliens that communicate through controlled brinicle formation. Time capsules, messages frozen in brinicle ice, preserved for millennia. These fictional explorations help us think about brinicles in new ways, sometimes inspiring real scientific inquiry. Artists have found inspiration in brinicles. Ice sculptures, artists recreate brinicle forms in galleries, capturing their beauty without their lethality. Sound compositions, musicians use recordings of brinicle formation, the crack of ice, the flow of brine, in compositions. Dance performances, choreographers interpret brinicle growth through movement. Digital art, computer artists simulate brinicle formation, creating impossible variations. Art helps us process the emotional impact of brinicles, transforming scientific phenomenon into human experience. Brinicles raise philosophical questions. Natural evil. Are brinicles evil? They cause suffering, but lack intention. Aesthetic ethics. Is it wrong to find beauty in deadly phenomena? Intervention ethics. Should we prevent brinicle deaths if we could? Knowledge ethics. Should disturbing natural phenomena be widely publicized? These questions don't have easy answers, but enrich our thinking about nature, beauty, and responsibility. I've never seen a brinicle in person, but I dream of it. In dreams I descend through polar water, watching a brinicle grow. It's simultaneously terrifying and beautiful, deadly and delicate. These dreams blend fear and fascination, the same mix brinicles evoke when awake. They represent nature's dual nature, creative and destructive, beautiful and terrible. When I teach others about brinicles, I see their worldview shift. The moment they understand ice growing downward, underwater, freezing creatures and spreading death, their expression changes. Wonder mixed with horror, fascination with revulsion. This reaction is valuable. It reminds us that nature exceeds our assumptions, that Earth still surprises us, that learning can be unsettling and exhilarating simultaneously. Knowing about brinicles changed how I see ice. Every icicle reminds me of brinicles. Every frozen pond makes me wonder what's happening beneath. Winter becomes more mysterious, more dangerous, more interesting. This perspective shift is permanent. Once you know about brinicles, you can't unknow them. They become part of your mental landscape, forever coloring how you see frozen water. Brinicles contribute to the global ocean conveyor belt, the thermohaline circulation that distributes heat worldwide. The dense brine they produce sinks to the ocean floor, flowing toward the equator, eventually rising and returning toward the poles. This circulation moderates global climate, distributes nutrients, affects weather patterns, influences marine ecosystems. Without processes like brinicle formation, ocean circulation would be fundamentally different, potentially making Earth uninhabitable. The deep water formation, influenced by brinicles, affects atmospheric patterns. Storm tracks, changes in ocean circulation, alter where storms form and travel. Precipitation patterns, ocean currents influenced by brinicles affect rainfall distribution. Temperature extremes, the ocean's heat distribution, partially controlled by brinicle-formed deep water, moderates temperature extremes. Seasonal variations, the timing and intensity of seasons are influenced by ocean circulation patterns. A change in brinicle formation could cascade through the climate system, affecting weather worldwide. Brinicles are part of the ocean's biological pump, the process that transports carbon from surface to deep ocean. Phytoplankton absorbs CO2 at the surface. They die and sink, or are eaten and excreted. Brinicles accelerate this sinking in polar regions. Carbon is sequestered in deep water, or sediments. This pump removes billions of tons of CO2 from the atmosphere annually. Brinicles make it more efficient in polar seas, contributing to climate regulation. As climate change accelerates, brinicle dynamics will change. Arctic changes. Thinner Arctic ice might produce smaller, more numerous brinicles. Antarctic shifts. Changing ice patterns could alter brinicle distribution around Antarctica. New locations. Brinicles might form in previously ice-free areas as polar conditions shift. Intensity variations. Warmer water might reduce individual brinicle size but increase formation frequency. These changes will cascade through ecosystems, affecting everything from microscopic organisms to whales. Future technology might harness brinicle principles. Controlled formation. We might create artificial brinicles for industrial cooling or desalination. Prevention systems. Underwater installations might use brinicle prevention technology. Energy harvesting. The temperature gradients in brinicles could generate electricity. Carbon sequestration. Artificial brinicles might enhance ocean carbon storage. Future exploration will reveal more about brinicles. Deep ocean surveys. Unexplored polar depths likely host unknown brinicle phenomena. Other worlds missions to Europa, Enceladus, and other icy moons might discover alien brinicles. Time-lapse studies. Long-term observation will reveal brinicle patterns over years or decades. Molecular analysis. Advanced techniques will decode the exact chemistry of brinicle formation. As night deepens around you, picture the darkness beneath polar ice. It's a different darkness, blue-green, filled with drifting particles, alive with invisible currents. In this darkness, brinicles grow unseen. They've been growing all day, all year, all century. They don't care about sunlight or human observation. They respond only to temperature and salinity, to physics and chemistry. Right now, creatures are dying, frozen by brinicles. A starfish, moving too slowly. An urchin, in the wrong place. A small fish, caught in spreading ice. These deaths are silent, witnessed by no one. They're part of the ocean's hidden violence, the deadly physics playing out beneath the ice. Tomorrow, scavengers will clean up, the ocean will continue. But tonight, death descends in frozen fingers. Despite everything we know, brinicles remain mysterious. We don't fully understand their formation triggers, their maximum potential, their role in ocean systems. They keep secrets beneath the ice. This mystery is valuable. It reminds us that Earth isn't fully known, that discovery continues, that wonder persists. Brinicles represent all the phenomena we haven't discovered, all the surprises Earth still holds. As your night ends and warmth returns with morning, remember the eternal cold where brinicles form. Your warmth is temporary and precious. The cold that creates brinicles is permanent and patient. This contrast makes morning more valuable. You wake to warmth most creatures never experience. You live in temperatures that would seem impossibly hot to brinicles' own organisms. There's comfort in distance from brinicles. They can't reach you. They're confined to the polar seas, requiring conditions that don't exist in most of Earth's oceans. Yet knowing they exist somewhere makes the world more interesting. Your planet has phenomena you'll likely never witness. Your oceans hide deaths you'll never see. Your world is stranger than daily experience suggests. You now carry knowledge of brinicles. This knowledge has weight, not physical but psychological. You know about underwater fingers of death. You understand ice that shouldn't exist. You comprehend beauty that kills. This knowledge changes you subtly. You're connected to Earth's extremes. You're aware of polar seas' hidden violence. You understand nature's capacity for deadly beauty. Brinicles exist at the extreme edge of what's possible, the intersection of temperature, salinity, and physics that barely allows their formation. They remind us that existence pushes boundaries, that life and phenomena exist at the very edges of possibility. We too exist at an edge, the narrow range of temperatures, pressures, and chemistry that allow human life. We're as precarious as brinicles, just in different ways. Brinicles create beauty without intention, death without malice. They're purely physical phenomena, following laws without consideration for consequences. This indifference is neither cruel nor kind. It simply is. The universe creates beautiful killers and deadly art without moral consideration. We're the ones who assign meaning to indifferent processes. Brinicles remind us that hidden worlds exist everywhere, beneath ice, in deep oceans, in places we rarely look. These worlds operate on different rules, host different life, create different phenomena. Every environment we think we know has hidden layers. Every familiar place has secret processes. Every investigated phenomenon has unexplored aspects. We discovered brinicles recently. Despite their ancient existence, they formed for millions of years, before we knew about them. This pattern repeats throughout science. Ancient phenomena newly discovered. Discovery continues. Right now, unknown phenomena occur worldwide. Future generations will wonder how we missed them. The age of discovery isn't over. It's just beginning. Brinicles are fingers of ice that grow downward from sea ice when super-saline brine meets seawater. They freeze everything they touch, creating trails of death across the seafloor. They're beautiful, deadly, and mysterious. They exist right now in polar seas, forming and killing, contributing to ocean circulation and climate regulation. They've existed for millions of years, and will continue as long as ice meets ocean. Knowing about brinicles expands awareness of Earth's extremes. They demonstrate that ice can grow downward. Beauty and death intertwine. Physics creates impossibilities. Discovery continues. Earth remains mysterious. Brinicles invite continued wonder about what else remains undiscovered, how physics creates phenomena, where life's boundaries lie, why beauty and danger connect, how Earth surprises us, You're now permanently connected to brinicles. This connection links you to polar seas. You'll probably never visit depths. You'll never witness beauty. You'll never see directly. Mysteries you'll never solve. Wonder that will never fade. Find peace in brinicles' existence. They demonstrate nature's continuing creativity, Earth's hidden complexity, physics' deadly beauty, discovery's ongoing nature, wonder's persistence. Sleep peacefully, knowing brinicles form in darkness. Wake gratefully, appreciating warmth and distance from polar death. Live curiously, wondering what other phenomena hide in plain sight. The brinicles continue, in polar darkness, creating frozen death, demonstrating impossible beauty, reminding us that Earth exceeds imagination, forever forming, forever reaching, forever killing, forever beautiful, forever mysterious. The icy fingers of death. The brinicles. To truly understand brinicles, we must follow a single drop of brine, from its birth to its deadly destination. This journey begins in summer, when seawater first freezes on the ocean surface. As ice crystals form, they exclude salt. Pure HATO crystallizes while sodium chloride and other salts are rejected. These salts don't disappear. They concentrate in pockets within the ice. Over weeks and months, these pockets merge, forming channels. Gravity pulls the dense brine downward through these channels, creating a network of salty veins within the ice. The brine's concentration increases as it descends, starting at 35 parts per thousand, normal seawater. It might reach 250 parts per thousand in the deepest channels. This hypersaline solution can remain liquid at -21 degrees Celsius or colder, temperatures that would freeze normal seawater solid. Instantly, winter arrives. The ice thickens, now several meters deep. The brine channels have become elaborate networks, like root systems made of liquid salt. Some channels dead-end in frozen pockets, others merge into larger conduits. A few find their way to the ice's bottom surface. Then comes the critical moment. Perhaps the ice shifts, creating a crack. Maybe tidal forces open a channel, or accumulated brine pressure finally breaks through. Whatever the trigger, a brine channel breaches the ice's lower surface. The brinicle is born. The moment brine meets seawater, a cascade of chemical reactions begins. Instant crystallization. Water molecules in the seawater immediately form ice crystals around the brine stream. This isn't normal freezing. It's shock crystallization, so rapid that the ice forms in unusual structures. Heat transfer. Each gram of water that freezes releases 334 joules of energy. This heat is immediately absorbed by the super-cold brine, which can accept enormous amounts of heat while remaining below seawater's freezing point. Salt diffusion. As the brine descends, salt slowly diffuses into surrounding water. But the process is slow. The brine maintains its deadly concentration for meters of descent. Density stratification. The descending brine creates layers of different densities. Each layer has slightly different temperature and salinity, creating a complex stratified column. Chemical precipitation. Some dissolved minerals precipitate out as temperatures and concentrations change, creating microscopic crystals within the brinicle ice. This chemical symphony plays out in seconds, creating structures that can last weeks. Brinicles leave unique isotopic signatures that scientists can detect long after they've melted. Oxygen isotopes. The ratio of O16 to O18 in brinicle ice differs from normal sea ice, recording the temperature of formation. Hydrogen isotopes. Deuterium concentrations reveal the brine's origin and concentration history. Carbon isotopes. Dissolved carbon in brinicle brine has distinctive isotope ratios, marking ancient brinicle sites in sediments. Sulfur isotopes. Sulfate in the brine undergoes isotopic fractionation, leaving traceable signatures. These isotopic fingerprints allow scientists to identify brinicle formation from millions of years ago, reading Earth's history in molecular ratios. Brinicles create distinct ecological zones that persist long after the brinicle itself has melted. The death zone, the immediate area where brinicles touch the seafloor. Nothing survives here during active brinicle formation. the seafloor becomes a graveyard of frozen creatures. The stress zone, surrounding the death zone, where organisms experience extreme cold and salinity but might survive. Creatures here show stress responses, reduced growth, altered behavior, cellular damage. The scavenger zone, where brinicle victims accumulate, attracting scavengers. Amphipods, isopods, and small fish congregate here, feeding on the frozen dead. The recovery zone, areas previously affected by brinicles, now recolonizing. Pioneer species establish first, followed by more complex communities. The refuge zone, nearby areas unaffected by brinicles, where organisms flee during formation events. Population densities spike here during brinicle season. After a brinicle event, ecological succession follows predictable patterns. Day 1-7, scavengers arrive, consuming frozen victims. Bacteria begin decomposing organic matter. Week 2-4, pioneer species colonize the cleared area. These are typically fast-growing, opportunistic organisms. Month 2-6, secondary colonizers arrive. More diverse species establish, creating three-dimensional habitat structure. Month 6-12, the community approaches its pre-brinicle composition, though some differences persist. Year 2+, full recovery, but the community might differ slightly from the original, shaped by the random nature of recolonization. This succession creates a mosaic of different aged patches on the seafloor, increasing overall biodiversity. Brinicles function as keystone phenomena. Their impact on ecosystems far exceeds their physical footprint. They control population densities of slow-moving species. They create opportunities for opportunistic species. They drive evolution of escape behaviors. They redistribute nutrients through victim decomposition. They create habitat heterogeneity. They maintain biodiversity by preventing competitive dominance. Remove brinicles from polar ecosystems, and the entire community structure would change. Species that currently coexist might compete to extinction. The seafloor might become dominated by a few successful species rather than supporting diverse communities. The first humans to witness brinicle formation were likely Inuit hunters, who noticed strange ice formations while fishing through sea ice. Traditional knowledge speaks of ice that grows wrong, and places where the sea freezes from within. Scientific discovery came much later. In 1962, oceanographer Seeley Martin was studying ice formation in a lab tank when he accidentally created conditions for brinicle formation. He watched, amazed, as ice grew downward through his saltwater tank, freezing everything it touched. Martin later wrote, "I thought my experiment had gone wrong. Ice isn't supposed to sink, but there it was, growing downward like some kind of frozen plant, killing the brine shrimp I'd added to the tank. It was simultaneously beautiful and disturbing." Commercial divers working in polar waters have terrifying brinicle encounters. Diver James Patterson, working on an underwater pipeline in the Beaufort Sea, describes his experience. "I saw what looked like a white curtain descending from the ice above. My first thought was, that's pretty. Then I realized it was growing toward me. The water around it was cloudy with ice crystals. A fish swam into it and just stopped, frozen instantly. I've never moved so fast in my life." Scientific divers face different challenges. Dr. Kristen O'Brien, studying brinicles for the National Science Foundation. "You have maybe 30 minutes before hypothermia becomes life-threatening. You're watching something that could kill you if you get too close. Your dry suit is the only thing between you and water that would freeze your blood. But the science is worth the risk. Seeing a brinicle form in nature is like watching physics become poetry." In Greenland, fishermen have incorporated brinicle awareness into their practices. They avoid certain areas during spring, when brinicle formation peaks. They've developed signs to predict brinicle formation, ice color changes, current patterns, even the behavior of seals. Norwegian folklore includes stories of ice serpents that descend from above to claim the unwary. These tales, likely inspired by brinicles, served as warnings about the dangers of winter fishing in certain areas. Russian polar researchers have a saying, "The ice has fingers, and they reach for the foolish." This refers both to brinicles and to the general dangers of polar ice, but brinicles are considered the most insidious threat, invisible, until too late. Under electron microscopes, brinicle ice reveals extraordinary complexity, dendritic structures. Ice crystals branch in fractal patterns, creating maximum surface area for heat exchange. Inclusion pockets. Tiny pockets of trapped brine create a Swiss cheese structure, making the ice less dense than pure ice. Crystal boundaries. Where different ice crystals meet, unique structures form, channels, ridges, and gaps that affect the ice's strength. Oriented growth. Crystals align along the direction of heat flow, creating directional strength properties. Defect networks. Crystal defects form regular patterns, potentially conducting heat and stress in predictable ways. This microscopic architecture determines macroscopic properties, why brinicles are strong enough to support themselves yet fragile enough to shatter at a touch. Brinicles host unique bacterial communities adapted to extreme conditions. Psychrophiles. Cold-loving bacteria that thrive at temperatures that would kill most life. Some remain active at -20 degrees Celsius, metabolizing inside the brinicle ice itself. Halophiles. Salt-loving bacteria that proliferate in the brine streams. They can survive salt concentrations that would desiccate normal cells. Cryoprotectant producers. Bacteria that produce antifreeze compounds, creating microenvironments where other organisms can survive. Biofilm formers. Communities that create protective slime layers, insulating themselves from the worst extremes. These bacteria aren't just surviving, they're thriving, using the extreme conditions as a niche, where competition is minimal. Within a brinicle, thousands of chemical microenvironments exist, pockets of different salinity, gradients of temperature, zones of varying pH, areas of different oxygen concentration, regions with unique mineral compositions. Each microenvironment could host different chemical reactions, different organisms, different physics. A brinicle isn't one environment but thousands, each just micrometers across, each with its own conditions. Brinicles connect multiple Earth systems. Hydrosphere. They transport water between ice and ocean, affecting ocean stratification. Cryosphere. They modify sea ice structure, influencing ice strength and longevity. Atmosphere. They affect gas exchange between ocean and air through ice. Biosphere. They shape ecosystems and drive evolution. Geosphere. They leave geological traces in seafloor sediments. Understanding brinicles requires understanding all these systems and their interactions. They're perfect examples of Earth system complexity. Simple in concept, complex in consequence. Brinicles participate in multiple feedback loops. Ice albedo feedback. Brinicles affect ice structure, changing how it reflects sunlight, influencing local heating and ice melt rates. Biological pump feedback. By killing organisms, brinicles affect the biological pump's efficiency, altering carbon sequestration rates. Circulation feedback. Dense brine from brinicles affects ocean circulation, which affects climate, which affects ice formation, which affects brinicle formation. Ecosystem feedback. Brinicles shape ecosystems which produce waste and remains that affect local chemistry, which influences future brinicle formation. These feedbacks mean brinicles aren't just responding to conditions, they're helping create future conditions. Climate scientists worry brinicles might be involved in tipping points. If warming reduces brinicle formation below a threshold, deep water formation might slow dramatically, potentially shutting down thermohaline circulation. If ice patterns change, brinicle zones might shift, causing ecosystem collapses in some areas and explosions in others. If brinicle-driven mixing decreases, ocean stratification might increase, reducing nutrient distribution and affecting global productivity. These tipping points could trigger rapid, irreversible changes in Earth's climate system. Brinicles have existed since Earth first had polar oceans with sea ice, EAs, at least 750 million years ago during the Cryogenian period, possibly earlier. Over geological time, they've contributed to mass extinctions in polar seas, influenced the evolution of cold water fauna, affected global ocean chemistry, left signatures in sedimentary rocks, shaped polar seafloor topography. The cumulative effect of trillions of brinicles over hundreds of millions of years has literally shaped our planet. Brinicle formation follows seasonal patterns. Autumn first brinicles form as new ice develops. They're typically small and short-lived. Winter, peak brinicle season. Large, long-lasting brinicles form. Maximum ecological impact. Spring, brinicle formation decreases, but individual brinicles might be larger due to accumulated brine. Summer, minimal brinicle formation. Ecosystems recover. Scavengers clean up remaining victims. These rhythms pulse through polar ecosystems like a deadly heartbeat, organizing life around predictable death. Even daily cycles affect brinicles. Tidal influences. High and low tides change pressure on sea ice, opening and closing brine channels. Temperature fluctuations. Even small air temperature changes affect brine production rates. Current variations. Daily current patterns influence where brinicles form and how they grow. Biological rhythms. Organisms' daily movements affect their vulnerability to brinicles. A brinicle that forms at high tide might be different from one forming at low tide, even in the same location. The actual moment when a brinicle kills is remarkably quick, 0-1 seconds. Organism contacts the expanding ice or super-cold brine, 1-3 seconds. Ice crystals form in extracellular fluid. Cells begin experiencing osmotic shock, 3-10 seconds. Intracellular ice formation begins. Cell membranes rupture. Organs fail, 10-30 seconds. Complete freezing. All biological processes cease. Death is complete, 30+ seconds. The ice sheet continues spreading, but the organism is already dead. This rapid death means no suffering in the conventional sense. The nervous system freezes before pain signals can be processed. Do creatures killed by brinicles suffer? It's a complex question. The freezing is so rapid that complex pain processing seems impossible. But simple organisms might experience something we can't comprehend. Not pain as we know it, but some form of distress. This raises questions about our moral relationship with natural processes. Should we care about starfish frozen by brinicles? Does their inability to escape make their death more tragic, or simply natural? Brinicles kill without purpose, create beauty without intention, drive evolution without goal. They're purely mechanical, yet their effects ripple through biological and geological systems for millions of years. This meaningless meaning pervades nature. Processes without purpose create purposes for other processes. Chaos generates order. Death enables life. Brinicles exemplify this paradox, purposeless phenomena that become purposeful through their consequences. Our observation of brinicles changes them. The lights and sounds of filming equipment might trigger or prevent formation. The heat from divers' bodies creates microcurrents that affect growth patterns, but more fundamentally, by observing and understanding brinicles, we change their meaning. They're no longer just natural phenomena, but symbols, metaphors, teaching tools. They've entered human consciousness and culture, acquiring meanings nature never intended. If consciousness emerges from complexity, could a brinicle system be conscious at some level? The chemical networks, feedback loops, and information processing in brinicle formation rival simple nervous systems in complexity. This seems absurd. Ice can't be conscious, but if consciousness is about information integration and response to stimuli, brinicles do both. They integrate information about temperature, salinity, and pressure. They respond by growing, branching, or stopping. We'll likely never know if there's something it's like to be a brinicle, but the question illuminates how little we understand consciousness, even in systems we think we comprehend. Contemporary artists have embraced brinicles as subjects and metaphors. Olafur Eliasson created an installation where artificial brinicles form in a gallery, growing and melting in cycles. Visitors watch death and beauty emerge from physics. Jennifer Rubel sculpted brinicle forms from sugar, which dissolve when viewers breathe on them, commenting on fragility and human impact on natural systems. Tomas Saraceno incorporated brinicle-inspired structures into his web-like installations, exploring connection and danger, beauty and death. These artistic interpretations help us process the emotional impact of brinicles, transforming scientific phenomena into human experiences. Composers have found inspiration in brinicles. Craig Veer composed Brinicle Suite, using recordings of ice formation and mathematical models of brinicle growth to generate musical structures. Christina Vonsu created ambient pieces inspired by the slow growth and sudden death of brinicle formation. Ben Frost incorporated the concept of freezing death into his dark ambient compositions, using the brinicle as a metaphor for isolation and inevitability. Music captures what words and images can't: the temporal nature of brinicles, their growth and destruction, their beauty and terror. Authors have woven brinicles into narratives. Kim Stanley Robinson featured brinicles in his novel Antarctica, using them as symbols of nature's indifference. Hugh Howey wrote a short story where brinicles on Europa hide alien life, using the deadly ice as protection. Liu Cixin referenced brinicle-like phenomena in his description of dark forest theory, beautiful structures that kill anything that approaches. Literature uses brinicles to explore themes of beauty and danger, knowledge and ignorance, life and death. Educators use brinicles to teach multiple concepts: physics, phase transitions, density, heat transfer, fluid dynamics, chemistry, solutions, crystallization, concentration gradients, biology, adaptation, evolution, ecosystem dynamics, earth science, ocean circulation, climate systems, ice dynamics, philosophy, beauty and danger, purpose and mechanism, knowledge and responsibility. Brinicles are perfect teaching tools because they're surprising, memorable, and connect multiple disciplines. Students consistently show strong reactions to learning about brinicles. I thought I understood ice. I was wrong. High school student, it made me realize how much we don't know about our own planet. Undergraduate, the ethics discussion about whether we should prevent brinicle deaths changed how I think about nature. Graduate student, these responses show brinicles' power to shift perspectives and inspire deeper thinking. Brinicles offer numerous research opportunities for students: modeling brinicle formation, mathematically, studying brinicle effects on local ecosystems, investigating brinicle formation in different solutions, exploring brinicle applications in technology, analyzing brinicle representations in culture. These projects teach scientific methods while exploring a phenomenon that still holds mysteries. Brinicles are fingers of ice that grow downward from sea ice. When super cold, super-saline brine meets warmer seawater, they freeze everything they touch, creating trails of death on the seafloor. They're physical phenomena following chemical and thermodynamic laws. They're also ecosystem engineers shaping polar communities, climate contributors affecting global circulation, evolutionary pressures driving adaptation, scientific mysteries still being solved, cultural symbols of beauty and death, philosophical challenges to our understanding. Brinicles mean different things to different observers, to scientists, natural phenomena to study and understand, to organisms, death from above, unpredictable and inevitable, to artists, inspiration for exploring beauty and danger, to philosophers, examples of purposeless purpose, to students, surprising connections between disciplines. To you, whatever meaning you create from knowing they exist. Brinicles teach. Physics creates phenomena beyond imagination. Beauty and death intertwine in nature. Earth still holds mysteries. Discovery continues. Extremes define possibilities. Connection spans. Scales knowledge brings responsibility. Wonder persists. Despite understanding brinicles form, when dense, super cold brine drains from sea ice into the ocean below, the brine freezes surrounding seawater, creating a tube of ice that grows downward. When it reaches the seafloor, it spreads in a web of ice, freezing and killing slow-moving creatures. They've existed for millions of years, shaping evolution, affecting climate, creating and destroying. We've known about them for decades, but still don't fully understand them. They inspire science, art, and philosophy. They kill without malice, create without intention, exist without purpose, yet serve many purposes. You now know. how brinicles form, why they're deadly, where they exist, when they grow, what they affect, how they've shaped Earth, why they matter, what they mean. This knowledge is yours forever. You can't unknow brinicles. They're part of your mental landscape now, coloring how you see ice, oceans, death, beauty, and Earth itself. Despite thousands of words explaining brinicles, mystery remains. We don't know all their effects. We can't predict exactly when they'll form. We haven't discovered all their variations. We don't understand all their implications. We can't fully recreate them. We haven't found all their locations. We don't know their future. This preserved wonder is valuable. Complete understanding would diminish brinicles. Mystery maintains their power to surprise, inspire, and disturb. You're forever connected to brinicles now. When you see ice, you'll remember ice that kills. When you consider the ocean, you'll think of frozen fingers reaching down. When you appreciate warmth, you'll recall the deadly cold. This connection links you to scientists studying them, organisms dying from them, artists inspired by them, future discoverers of similar phenomena, everyone who knows about them, the Earth that creates them. Find peace in brinicles. They're part of Earth's wholeness. They belong here as much as flowers or sunsets. They're not mistakes or horrors, but expressions of physics, chemistry, and thermodynamics. Accept them. Earth has fingers of death, and that's okay. Beauty kills, and that's natural. Ice grows downward, and that's possible. Your planet is stranger than you imagined, and that's wonderful. Return to sleep, knowing brinicles are forming right now. Creatures are dying, frozen instantly. Ice is growing where it shouldn't. Beauty and death dance together. Earth keeps creating surprises. Discovery never ends. Wonder persists. Mystery remains. Brinicles exist. They're real. They're happening now. In polar seas, beneath ice, in darkness we'll never see. Fingers of death descend. They've been descending for millions of years. They'll continue for millions more. They don't care that we've discovered them. They don't need our understanding. They simply are, following physics, creating death, demonstrating beauty, defying intuition. But we're changed by knowing they exist. Our world is larger, stranger, more dangerous, more beautiful. We're connected to extremes we'll never experience. Deaths will never die. Cold will never feel. Sleep peacefully in warmth. Dream of ice that grows downward. Wake grateful for distance from polar death. Live knowing Earth exceeds imagination. The brinicles continue forever forming, forever reaching, forever killing, forever beautiful, forever mysterious, forever. The icy fingers of death, reaching through dark water, freezing life into stillness, creating deadly beauty. Brinicles